The pre-built model that we're going to go through today focuses on using foundation drainage blankets for managing the groundwater around structures. So in this example that you've got here, we've got a foundation, there's a gravel blanket underneath, and then you have collector drains located within the gravel, which collect the groundwater and that then gets pumped out. This lowers the groundwater level around your foundation. So these produce drainage and they reduce risks such as water infiltration and foundation damage. The pre-built model that we provide, it needs to be thought of like a design sandbox. So it's for testing your assumptions, exploring how sensitive the model is to changes, and making quick adjustments when your plans evolve. It can be used in this situation to determine the answers to questions such as what permeability and thickness does the drainage blanket need to be, how much water is going to flow through the blanket, what impact does that have on the surrounding groundwater levels, how will varying the aquifer conditions affect drainage performance, and what's the optimal spacing of these collector drains. So we're next going to open Anaxim. Here we've got Anaxim open and we are going to load the pre-built model. And I'm just going to make a plot of the model elements only. Right. So this is what our pre-built model looks like. And the aim of this video is to show you how you can customize it to wherever your project site is and change the parameters so that it becomes specific to your project. This model we've got on the outside here, these green lines around the border, that's our outside boundary, which is quite far away from our area of interest in the middle. The model is centered around sort of 0, 0. You can see that in the coordinates on the left. And this means it should be easy for us to shift it to wherever the actual project is. If I zoom in, we've got a L-shaped building in the middle, which is what we're trying to drain the foundations of. The little green lines here, they are the collector drains. The blue circle, slightly outside of the building, is showing an area where we want a bit higher resolution of a model. So the first thing for us to do is to load a base map of our actual project site. So I'm going to go to plot input, it's under what to plot. At the moment there's no base map selected, so let's add in, I've got a DXF file. And you need to change it from none to either colour or grey. I often have to save the model quite frequently through the process. So we're going to call this a customized model. And then if we make the plot again, if I zoom out, I have to zoom out quite far, this is where our background map has come. So in our real world example, we have a building, an excavation and another building, and we wish to dewater the foundations around this excavation. So the next thing to do is to shift the entire model from where it currently is, centered on 0, 0, to some coordinates that more represent where our project is. And that is closer to 10,000, 10,000. So if we go up to model input, shift model, I can just type that in. It's asking me to replot, and immediately all of the model elements have been moved straight over. The next thing we need to do is to modify the domains. So go to model input, domains, and then all our domains are under confined and or unconfined. At the moment, there's 4 domains, so there's 3 layers overall in the model. And then in our area of interest under the building, we've got an additional drain layer. Now these elevations have come from the pre-built model and we need to modify them for our sort of customized scenario. So our top elevation is going to become 33,
to 28, then layer 28 to 27, 27 to 26. And the drain layer, which is the gravel blanket, will be 29 to 28. These all need to be changed to be consistent with whatever your project needs are. The average head as well, that needs to be changed, so about 30.6 works for us. So next we need to change the horizontal and the vertical conductivities. These are initially at 0.5 and we're changing it to 0.8. And in the gravel layer, which is more conductive, that is going to 8. The vertical we're just setting as 1/10 of the horizontal. So we're going to save that and make the plot again. The next thing we need to do is we need to review whether we think that the external boundary is at a great enough distance away from our area of interest. At the moment this looks okay, but it's something you can always change afterwards as well. So that is set under model inputs, line boundaries, head specified, external with gradient. And we've got one of these for each of the 3 layers, and our radius is 1,000. So if you needed to change that to be greater, you could sort of make the radius 2,000. Our next thing is to change the internal domain boundary. Now if we zoom in on here, the internal domain is what is defining the sort of difference between the gravel blanket layer under the building and the layers that are outside of that gravel blanket. So at the moment, that interdomain boundary is the L-shaped building you can see, and we need to change it to match our proposed excavation. We go to model input, it's line boundaries, and it's interdomain. So we want to edit the coordinates. At the moment, that represents the L shape, and I'm just going to copy across some values that represent a more square. There we go. If we save that again, make the plot. There we go. I'll zoom back in, and you can see that that outside L-shaped building has now changed to be a square building, or representing the excavation. I'm going to set the plot window to the current view so that it doesn't keep resizing every time we replot. The next task is to look at the vertical flow, and in Anaxim the vertical flow is defined where we've got these little points. They're called spatially variable area sinks. Now if we go to model input, area source sink, spatially variable domain, you'll see here we have 2 of them. They've both got the same node spacing actually, so that all looks okay. And then we've also got, if we go under polygon, we've got extra spaz polygon, which has got a smaller node spacing, so you get a higher density of points. If we go back to the plot, that's this polygon here where we've got the higher density of little crosses inside versus outside, giving us a higher definition within this polygon. Now we need to realign where these drains are because they are still representing the old L-shaped building. The drains are under line boundaries and head specified. So we've got a whole range of them here, and we need to change them. To change them, we need to edit the coordinates, but also the level that we are defining the water to be at within the drains. If you remember, our average head was 30.6 and the drain layer was between 29 and 28 metres. So really we want the head levels in the drain to be at the base of the drainage blanket so that we're extracting as much water from it as possible. So I'm going to change those all to 28. Now, rather than editing the coordinates here, it might just be easier to drag and drop them in the interface. So I'll just save that. We'll remake the plot. There we are. And now we're going to try and drag these. I think I'm just going to go with 3 long ones horizontally. Now if I just record what these names were, that was D2, D3 and D4, and we'll go and delete the other ones. We do save, make the plot, we'll just make sure we got rid of the right ones. Yep, there we go. Now I haven't been very precise, you could put in the exact coordinates and have them equally distanced. But as an initial tool to find out whether you need 3 or 5, this will be a pretty good starting point. We're now ready to solve the model. So if we go to solve here, this is telling us there's 3,418 equations to solve, and it's currently going through the solve process. It's solved within 7 iterations. So we can now go to the make plot and we've got some contours showing. If we put our cursor near the middle on the left hand side, you can see what water level we have decreased down to. So that is where it says head on the left bar. So that's about 28.1, 28.2. We're getting actually quite close to the 28 sort of target that we put into the collector drains. And outside of that, the head levels are increasing radially. We can customize the contours a bit so that we don't get the contours coming out at very random numbers. We go to the plot input and contour settings. If we set a minimum, I think let's go for 27. And if we set an increment of 0.25, I'll save that. We don't need to resolve because it's just a visualization setting. So we can make a plot of the same level again. And straight away, it looks a bit tidier, although perhaps we've gone for slightly too large a contour because we can't see any of the sort of detail in here. If we redo that, contour settings, and let's go to an increment of 0.1. Make the plot. There, that's a bit better. So at the moment we are plotting model level 1, but we can also equally choose the level and plot a different level. So we get a slightly different result. You may also want to know what the discharges were along the collector drains. So we can go to analysis. There were head specified line boundaries, and we can write the discharges to the run log. And here we have got the outputs. Now these values don't have units associated with them, but they will be consistent to the units that you have been using throughout the model. So if you've got a length unit that you've used or a time unit, then this will be the length unit cubed over time. So in meters and days, that'd be meters cubed per day. The negative value means that it is being discharged out of the model.